Reinforced concrete has greater strength than unreinforced concrete because the steel in the reinforced section can be used to carry large tensile forces, as will be demonstrated in this laboratory testing. Concrete can withstand very large stresses under uniaxial compressive forces. However, the failures observed are not compressive in nature, but failures along shear planes where maximum tensile forces occur. This sudden type of failure is unacceptable in structural applications, and most concrete is reinforced with steel to increase its strength and ductility. In practical applications, bars are added in a steel cage pattern to cross potential planes of tensile failure. Steel reinforcement serves to limit crack formation and crack widths, increasing the life of the structure. De-icing salts and other chemicals are impeded from penetrating and corroding the reinforcing steel. Stiffness of the structural members is maintained, and long-term deflections are reduced. And the aesthetic appearance of concrete structures is improved. In this video, we will conduct tests to determine concrete tensile strength and compare reinforced with unreinforced concrete. In concrete, a very thin, weak layer between the mortar and the aggregate, called the interfacial transition zone, results in very low tensile strengths. Because the design of common concretes is driven by the need to maximize the aggregate content and minimize the mortar volume, the particle spacing is very small, with up to 40% of the mortar volume made up of the weaker ITZ material. The local larger water-to-cement ratio during mixing and hardening in the interface area results in weaker crystal structure in the ITZ. This condition, coupled with the stress concentrations around the irregular aggregate particles, leads to preferential crack growth in this area. To test the tensile properties of concrete, a method known as the split cylinder test is often used. A compressive force is applied, resulting in a uniform horizontal tensile stress in locations away from the applied load. A correlation is typically seen between the tensile and compressive strengths, although typical coefficients of variation for these relationships are high. Another method used is a 4-point bending test configuration. In this test, the top fiber is in compression and the bottom one in tension. When the tensile strength is reached at the bottom, a crack forms, causing immediate failure. A similar correlation of tensile and compressive strengths is seen for this test. The beam test results in predictions of tensile capacity generally 30 to 50% larger than the split tension test. But because cracking in many concrete elements is due to flexure, the values from the beam tests are typically used in design. To compare unreinforced to reinforced concrete, steel bars are placed in the bottom tensile side of a beam and then tested. In the next section, we will measure the tensile strength of unreinforced concrete using the split tension test and compare the tensile strength of unreinforced and reinforced concrete using the beam tension test. For these tests, use the sample cylinders that were prepared in our video discussing fresh concrete. Use a thin strip of balsa wood and a stiff steel bar to help distribute the loads uniformly from the cylindrical loading heads in the compression testing machine. Draw a line along the diameter on each end of the specimen bisecting the cylinder. Next, center one wooden strip and stiff steel bar along the center of the lower bearing block of the testing machine. Now place the cylinder on the strip and align so that the lines marked on the ends of the specimen are vertical and centered over the strip. Next, place the second wooden strip and steel bar lengthwise on top of the cylinder. Then lower the upper loading head of the testing machine until the assembly is secured in the machine. Apply the compressive load slowly and continuously until the specimen fails in split tension. Finally, record the maximum applied load. Examine the fracture surface and estimate the percentage of aggregate that has fractured. Repeat this process for the second cylinder to get an idea of the variation. Construct two concrete beams, one without reinforcement and one reinforced with two number 3 bars located about 0.5 inches from the bottom. The bars have hooks at the ends to prevent a bar pull-out failure. Both beams are 4-inch by 4-inch in cross-section, with 16 inches in unsupported length. Carefully lift the concrete beam and install it into the setup. Then install a 4-point bending test apparatus in the testing machine as shown. The test is called a 4-point bending test because we have 2 supports at the ends and 2 load points at the third point. Turn on the testing machine and activate the software to read load and deformations. Next, apply the compressive load slowly and continuously until the specimen fails. Record the maximum applied load. Finally, examine the fracture surface and estimate the percentage of aggregate that has fractured. Repeat the same protocol for the reinforced concrete beam. In this case, steel reinforcement at the bottom or tensile side of the beam prevents sudden brittle failures. As the concrete begins to crack, the steel will begin to take up the tensile forces. This technique works as long as the steel bars, which have surface deformations to help them transfer forces from the concrete, are properly anchored. Calculate the tensile strength for the maximum compressive load reached during the split tensile test. For these tests, the average was 388 psi with a standard deviation of 22.2 psi. Calculate the tensile strength for the maximum compressive load reached during the beam tensile test. For these tests, the average was 522.9 psi. We can compare the unreinforced and reinforced concrete beams by looking at their load deflection curves. Initially, both beams followed a similar path, with slight differences in initial stiffness probably due to changes in support conditions. The unreinforced beam failed as soon as initial cracking occurred at a load of about 450 pounds, a load close to the predicted tensile strength. The reinforced beam cracked at a higher load but regained its strength quickly, albeit at a lower overall stiffness. The load continues to increase until the steel begins to yield, after which the curve begins to flatten. Because steel is very ductile and strain hardens, failure occurs at large deformations. A comparison of the two curves shows the dramatic difference in performance. The difference in strength is very large, but it should be noted that this is related to the area of steel used. Now that you appreciate the need for steel reinforcement in concrete, let's look at a couple of common applications. Using just 1 to 1.5% steel over the area of the concrete cross-section can make concrete structures that are economical, safe, and provide good serviceability. Many football stadiums, such as Soldier Field in Chicago, owe their unique forms to reinforced concrete. Frank Lloyd Wright brought reinforced concrete into the world of modern-day architecture. Making use of its ability to maintain its integrity in unsupported cantilevers, Wright used the material in some of his greatest works, including Falling Water in Pennsylvania. You've just watched Jove's introduction to compression tests on hardened concrete in tension. You should now understand the brittle nature of tensile failures in concrete and know the standard laboratory tests for determining the strength of unreinforced and reinforced concrete under tension. Thanks for watching.